invitation. It's always a pleasure to speak about what I do to the crowds at Dalhousie, and especially Dalhousie Oceanography. Yeah, so I never was really into the ocean part of oceanography. I was always more interested in what happens beneath it. And today I'm going to talk about a major geodynamic issue or problem that has to do with the rise, the timing, and especially the timing of the rise of the Tibetan plateau, and how we recently have provided new constraint and also some modeling that attempts to address that question. I know that my former PhD supervisor and mentor, Chris, and his wife, Becky Jemison, Chris Bowman and Becky Jemison, have worked quite a lot on related problems, and which I had never done before. So I'm quite pleased to kind of show my contribution to this issue and problem of a recent past. Oh, I must obviously say that, you see, I'm not even the first author on this paper. This is the work of that I've done with two colleagues, Xiaoming Shen, who comes from the National Institute of Natural Hazards in Beijing, and Xiaoping Yuan, who is a postdoc in my group here at the GFZ in Potsdam. And Xiaoming is here on a visit on a one-year sabbatical, and is the reason we worked on this problem. So let me first tell you why we work. A lot of us work on the Tibetan plateau. It's an amazing region. It's one of the presents the highest topographies on Earth along its southern side, the Himalayan mountains. But it's also a very strange area, which, even though it's very high in altitude, about 5,000 meters on average, it has a very low relief, and that's why it's called a plateau. It also has a very complex geological history, which has been the center of much debate over the years, and I will summarize this in a few minutes. It's strongly linked to the Asian monsoon, its intensity, and its onset. And as most of you work in the climate evolution of the Earth, you know how important these high elevation, low relief areas have on controlling the circulation pattern in the atmosphere. But recently, it's also been shown, or not recently, but a lot of focus has been put on the effect of these mountainous regions, and especially these high elevation regions that are characterized by margins that are highly dissected as what they call biodiversity pumps. And I will come back to this at the end of my presentation, but it's clear that there is obviously a strong link between biodiversity at the Earth's surface with climate. But the second most important feature is relief itself. And I will, as I said, will show you how important, or it's been documented, how important the Tibetan plateau and especially its margin is in controlling biodiversity, especially here as shown by this paper by Ding et al. For alpine flora. But I will show you how constraining the timing of uplift of the plateau, and especially its southeastern margin here called the Huangduan mountains, is for biodiversity in the region, but also in major other parts of Asia. And finally, the plateau is the source area for most of the large Asian rivers. And of course, these rivers control a lot of the economic and agricultural activity in this part of the world, but also there's a lot of debate on how far in the past have these rivers been flowing like they do today, and potentially have been the subject of captures and drainage reorganization in the recent geological past. So all these kind of reasons why we think the plateau is an important feature worth studying, and especially the timing of its uplift and when it reached its present day geometry or topography. So I'm going to very briefly report you the various models or ID concepts that have been put forward for the formation and the evolution of the plateau. In the early days, in the 70s, Peter Molnar and Paul Taponnier looked at the plateau as the result of the indentation of India into Asia, causing the continental Asian continent to behave like a brittle plastic material. And they associated the deformation and the formation of large faults and structures in Asia, and assimilated them to slip lines that form when a plastic or a brittle material is deforming in this way. More recent work here by Repluma and Taponnier tried to reconstruct the evolution. I'll play this little animation again. The evolution of especially Southeast Asia, and you see that they regard the deformation as due to the rotation and sliding of lithospheric blocks along lithospheric scale structures or faults, mostly strike slip faults. Now, a completely different idea was proposed by England and Mackenzie, which regard the lithosphere as a thin viscous sheet. And again, due to the indentation of India into Asia, this viscous material, thin viscous layer deforms, and they've shown actually that how much thickening versus how much spreading of the continent takes place can be measured by a dimensionless number called the Argon number. And they showed that, from the present day geometry of the Tibetan plateau, you can predict the value of that Argon number. And it tells us something about how the viscosity, something about the viscosity of the lithosphere, the average viscosity, and its ability to respond to a gradient in topography and in thickening, in crustal thickness. Other models too that simply said that the plateau experienced a very rapid phase of uplift. This is a vertical cross-section when the lithospheric root, so the part of the lithosphere that's been thickened during the collision, actually detached. And that must suddenly increase the uplift or the topography of the plateau and may cause all sorts of, maybe the cause, for example, for the strengthening of the monsoon about 8 million years or 10 million years ago, but also would result in a very highly compressive state of stress for the plates surrounding the plateau, including the Indian oceanic plate, which may have experienced at the time something very rare for an ocean, a shortening and thrusting, as evidenced here by reflection seismic data, seismic reflection data. Another more recent model sees the expansion of the plateau, especially in southeastern part here, due to lower crustal flow. So in this model, you create a plateau, and that plateau is in a potential energy and wants to flow out, and it does it by inflating the crust, and the lower crust, by propagation of material of hot, viscous material from under the plateau into the surrounding areas. And the reason this model was invoked is because it tried to explain the uplift of this region, which is seen without having too much evidence for deformation of that region. So it's a kind of a contradictory view with the early model by Taponnier, that these faults don't have a major role, these big structural faults. They really, the deformation is happening without much upper crustal deformation. So the uplift is happening without much crustal deformation. Even more recently, another model, especially for this part of the southeastern part of the plateau here, in which again it's a gravitational but not inflation of the crust here, but a flow of the upper crust across this gradient in topography caused by the growth of the inner part of the plateau. And they use evidence to constrain the model of this very spectacular and unique velocity field that has been evidenced by GPS measurements that shows how the rock seems to wrap around here, around the eastern syntax of the Himalayas. So this is the part of India, the bit of India, the edge of India that's running into Asia. And you see how the crust seems to be flowing from high elevation to low elevation. Finally, and I will stop with all these models, this even more recent one, which also points to the fact that, you know, when India collided with Asia, it deformed a very large subduction zone, and that there are remnants of that subduction zone under what is today Myanmar, or former Burma here, and we know there is a small or ancient subduction zone that may be the reason, by retreating that subduction zone, may be the reason for this velocity field that seems to wrap around the syntax. And they did a complex model, a 3D visco elastoplastic model of this collision to actually show that it could be the case. The important thing that I want to remember of all these models, and the one thing they seem to all have in common, is that, you know, the plateau has been growing in southeastern Tibet, has been growing southwards, and is still growing or highly actively deforming today. So I want to contrast that with some constraint we have also from paleoaltimetry data. So paleoaltimetry, as you may know, is a way we have to measure the elevation, the past elevation of the Earth. It's a very imprecise method. It gives us rough estimates of past elevation, and it's based on, there are many methods, but the most commonly used one is to look at the stable isotope, especially here of oxygen, in sediments. Why? Because as an air mass is pushed above a relief and a topography, it causes a decrease in pressure and therefore condensation and precipitation. But we know that the heavier isotope of oxygen, or the water, you know, that has a higher isotope of oxygen, tend to precipitate earlier than the light water. And therefore, if you go today at the Earth's surface and measure this ratio of oxygen isotopes, you see a relatively good correlation with present day elevation. So if we now go into sediments that were deposited in the past and manage to recover this isotopic ratio, which is a signature of the rain that precipitated at that location or upstream from that location, we can get an estimate, a very imprecise estimate of the elevation of that lake sediment in the past. And what is interesting is, if you look at the part of southeastern Tibet that we are interested in, and this is the topographic profile here going down the side of the plateau there, and we look at the present day topography and the paleo estimates that date mostly here from Eocene sediments, so that's about 20 or so million years ago. You see that especially in the higher part of the plateau, it shows that the plateau seems to already have been present, or its current day altitude at the time. And there's an unpublished but more complete report of such studies in a paper by Penny and Copley. And you can see these various sites here that are reported here. The blue lines represent the present day elevation, and the dots, the plots here, the data shows estimates using oxygen isotope. And you see that, at least by the middle Miocene, something like 10 million years ago, the data suggests that the present day elevation was reached almost everywhere along this profile. So if you want to summarize the paleo elevation, paleoaltimetry data, it seems to suggest that the plateau may have expanded sometime in the past, but that it must have reached its present day elevation, at least in the mid-Miocene. They could have even done that before, which is very much in contrast with most of the models that have been proposed. Now we have other constraints that I want to go through and talk about before I go and show you our new data. Is constraint coming from low temperature thermochronology. So for those of you who are not specialists, and I assume there must be quite a few, low temperature thermochronology tells us something about the history of exhumation of a rock that we collect in the surface in the as it is exhumed towards the surface. But the way we get this information is by, it tells an age that corresponds to the time at which the rock went through a given temperature. And as we call it here, low temperature data, these are temperature in the range of about 100 or so degrees Celsius. And we have different thermochronometers that allow us to reconstruct the path that the rock particle, or the temperature path that the rock particle has experienced in the past before reaching the surface. We can also collect samples at various elevation, and if we compare the elevation of the sample with its age, the slope of that relationship is telling us something directly about the rate at which the rocks are exhumed to the surface. So, with some, you have to be very cautious because it's not a one-to-one relationship. But if you measure ages of rocks along a vertical profile and you plot that in elevation age relationship, the slope here is a proxy, reasonably good proxy for the erosion rate at the time, of the mean age of the rocks. So, I'm going to quickly go through 3 or 4 studies that have used low temperature thermochronology in that region to show you the diversities in ways these ages have been interpreted. So this is an example from Wime et al. That shows this, relatively rapid exhumation about 5 or 8 million years ago in this region here. And I'm going to focus here on data taken in these 3 large rivers, the Yangtze, Mekong, and Salween, which cross this region here. And you see that they predict an exhumation rate of about, as I said, 400 meters per million years, somewhere between 5 and 10 million years ago. And that was taken as evidence for uplift at that time, and evidence that the plateau was actively growing and expanding southward. There's another more data from roughly the same area. And again, I'm not going to go into detail, but just to give you the interpretation that was given by Nie et al., it shows an apparent correlation between the periods of rapid cooling of the rocks as they go to the surface and intensification of monsoonal activity in the past. So they look at age here at the bottom. And so that led these authors to conclude that really the exhumation rate or erosion rate of the rocks towards the surface is strongly dictated by the climate. As it rains more, rivers become more at a higher erosive power, and therefore erosion is faster. Another maybe in my view more interesting studies looking again at the same region shows when you interpret the data in the way they decided on with the method they have used, shows as you go, so this is time from old to present day. And these contours are estimates of the erosion rates at this location as a function of time. And what you can see, which is very strange, and I'll explain to you in a minute why, it seems that the locus of maximum and fastest erosion is migrating northward. And I'll explain to you which kind of poses a problem later. But they see this migration and they try to interpret it as maybe the propagation of a nick point. So basically this region of high relief in a river that tends to migrate upwards along a river profile, but they fail to do so. They reckon that the rate at which this nick point is migrating is way too slow, and it cannot be used. Nick point migration cannot be used to explain the data. And finally, there's another study along another part of the river, but very close to an offset in one of these major strike slip faults. And the way these authors interpret their observation, again, a rapid and maybe two-step, two-phase exhumation phase here or period in the data between, again, since the late Miocene, they interpret it as an exhumation that's associated with rapid uplift due to this step in the fault, which causes some kind of a restraining band here that causes rapid uplift and exhumation. So in other words, still showing this rapid cooling in the late Miocene, but interpreted as a purely local effect associated with fault motion, and not the propagation or of the plateau or its growth. So low temperature thermochronology, many studies, but what the observation is that there's evidence for fast exhumation since the late Miocene, that usually the younger stages are found in the region of higher slope, but the important thing in the river, but the important thing, and I will come back to this point later, it seems to show that the locus of fast exhumation is moving northward since the late Miocene. And I go here through the list of all the interpretations that I already cite you, and I'm not going to go through again this interpretation. But what I find they have in common is that they're all local, that they're trying to interpret the data where it was taken. And two things that it avoids any kind of regional interpretation, looking at the pattern and the data in both space and time. And maybe more importantly, they do not take into account what I call the horizontal advection of rocks, which is strongly suggested to us by the GPS data. So the fact that rocks not only go up and down towards the surface, but also experience horizontal motion during their exhumation. And now let me quickly show you this GPS data that I talked about. And so you see this is an area of very much a great interest to many. So there's a large density of GPS stations that have been there for more than 20 years or almost 20 years. And so the data and the estimates of rock velocity that have been derived from here are very, are thought to be very reliable. And what I found very interesting is this impression that you see from the field that really the Tibetan plateau is flowing out through this narrow conduit stuck between the syntax and a rigid block, or a block that's not deforming the Sichuan basin here. The data explains is quite consistent with the large-scale structures that are seen, in the geology. For example, here the major southward bounding faults of the Longmen-Shan are a region of very rapid or gradient in velocity, which suggests that there is exhumation along the Longmen-Shan and a relatively deformed Sichuan basin here. And that's been shown to be the case by many authors now. But also you can see that there is a very strong strike slip component in the velocity field derived from the GPS data that corresponds to this very major structure here that's been there and has been documented and for existing in the area for many millions of years. And if we look also at the other side here of these regions of southward flow of the lithosphere near the border with Myanmar, we also see that the GPS data is very much consistent, provide estimates of strike slip deformations, motion along the structure here that is very consistent with the rates, the strike slip rate derived from geological long-term deformation. So we can be quite confident with that this present-day surface motion that is derived from the GPS data is consistent with the large-scale fault and the long-term deformation, and therefore can be said as a reasonable proxy for the long-term velocity of rocks over maybe a few million years in this part of the world. So this is the end of kind of my introduction. It's a bit long, but I wanted to clearly state what the issue is there and the breadth of data that exists to try to constrain the recent, let's say the last 10 million years of growth, topographic growth of the plateau, and also try to motivate you in saying how important a problem it is and highly debated issue. So my colleague Xiaoming Shen went back to the field to collect more rocks, to do more low temperature thermochronological analysis, and he took great advantage of the extreme relief that exist in this part of the year. So here we have rivers that flow in valleys, and where the relief between the bottom of the valley and the top of the adjacent hill, which is maybe more like a mountain here, is of the orders of 4,000 kilometers in the northern part of the area here along the Mekong. But still, even in the southern part where the topography is less, the relief is still of the order of several thousand meters. And so he collected age elevation transects, so transects, rocks along vertical transects at 4 locations here, Lushui, Fugong, Gongchang, and Yanyin, and processed the rocks to in his lab, which is a very efficient and well-funded lab, providing good, high-quality data, and especially a very large number of grains can be analyzed on a given sample to give good estimates of the age and its reliability. Now, these are the ages that you obtain for the 4 locations, sorry. And what I've plotted here is the data, age measured with its uncertainty as a function of elevation. And we do this very simple interpretation first, looking at the slope of this relationship. And what I found remarkable is that at every location, you see the same, almost exactly the same apparent exhumation rate of about 0.75 or so meter or millimeter per million year or kilometer, sorry, millimeter per year or kilometer per million year. But what is fascinating too is that we also see that the younger stages are in the north and the older stages are in the south. So this means that in Luoxiu, we've seen past exhumation about 7-8 million years ago. In Fugong, this happened about 5 million years ago. And in the north, in Gongchuan and Yangjing, that's happened much more recently, 2.5 million years ago. Now, this is very consistent with the observation already made by Yang on a reduced data set, and one in which they didn't have so many or so good age elevation relationship. But it also implies that, as the erosion rate goes northward with time, and if we know that erosion takes place where slope is the highest, it's almost something that we're quite confident about. So if we assume that, it's a reasonable assumption to make that the slope is the highest where the plateau edge is. If we want a first-hand, explanation of that data, what we come up with is that in the last 10 million years, the plateau must have actually shrunk back to the north, or at most remain in its present-day configuration, and maybe some kind of a nick point on the river itself, carved back, or the 3 rivers carved back into the plateau. But it's really difficult to explain the data by assuming that over the last 10 million years, the plateau has been expanding southwards, and its margin has moved southwards. This would have implied that we should see the opposite of what we see, that the youngest profile should be in the south and not in the north, as seen here. So this has led to kind of revisiting all the models and try to find a way to reconcile one model or some models with the low temperature thermochronological data, but also trying to take into account all the other constraints from paleoaltimetry, from GPS data, and as you will see, from even other data. So this is what we have, the situation we have. We have the data that Zhao Mingshen collected at this various site, but also all the pre-existing data, which we have all combined into a single data set. We have constraint from GPS data, we have constraint from the tectonics, the faults, and we also have constraint from the Moho geometry, which may influence the way the rocks are deforming or the crust is evolving, deforming, and to create the plateau. So what this is the data, the thermochronological data. You see there's quite a lot more than what collected by Zhao Ming. And what's interesting, if you plot it this way, simply as a function of latitude, you see clearly this trend in ages getting from old to young to the south towards the region of present-day fasted exhumation. And as if you go further north, then they become old again. And this is true for various systems. I'm not going to go into detail of the various systems we have used that have different closure temperature, but it's true for all systems. What we're going to make an assumption which came up to me and Zhao Ming when we looked at that data. It really looks like, if we go back, sorry, to this data, it really looks like, we have a zone, which is now somewhere here in the north, of rapid exhumation that brings the rocks to the surface, and then they're basically advected southwards. And so there's some kind of a cruncher of rocks that is fixed somewhere in space, and then the rocks go through it. North of it, they haven't been exhumed to the surface, so the edges are very old. The age is determined by another process, an older process. And as they go through that, they are reset, because they're exhumed there, and are advected southwards, and the age is frozen in the rocks. So for this, we make this assumption very simple assumption that the topography, the present day geometry of the plateau is constant. And we make the assumption, very abrupt, radical assumption that the topography has not changed over the last 10 million years. Of course, it's an approximation. We know that the details of the topography must have changed through time. But to simplify our model, we will assume that the topography, this is the north, this is the south, has remained fixed with respect to Asia. With respect to the topography of the plateau has remained fixed with respect to Eurasia. And what we're going to assume is that with this fixed topography, rocks are actually, due to the topographic difference between the plateau and the low-lying areas to the south, are actually flowing southwards. And they flow up across the ramp, which we don't really know its geometry. And doing so, they're advected southward, but also forced to cross the surface at some location. Okay? So what we're going to do is going to use a model that I have developed that solves the very basic and well-known equation of heat transfer. And we're going to assume that heat can be transported or transferred in two ways, by conduction and by advection. Advection means that by the movement of rocks as they are carried from depth towards the surface. And they can be carried vertically, but also horizontally. And we solve that equation. And then what we do for 10 million years under a given scenario, for a given ramp geometry, a given topography, and a given velocity of the rocks. And once we have computed that through 10 million years of evolution, we can work back for any rock at the surface here. We can work back its thermal history that it has experienced during that scenario. And from that thermal history, we can predict an age for the various systems for which we have an age. So we can predict ages that we can then compare to the observed ages. And what we're going to do here is run this model through an optimization method by running not 1 or 10 models, but running tens of thousands of models, in this case about 35,000 models, varying the geometry of the ramp, varying the velocity at which the rocks are fed through the crust here, and varying the geothermal gradient, because we don't know what it is, what it was in the past, and even what it is today with accuracy. So we run these tens of thousands of models by also using an optimization method to try to find the model parameters, so the geothermal gradient, the geometry of the ramp, and the velocity that best fit and represent the data. And so we see here that the geometry of the ramp, we determine it by fixing 2 points here, this point here, this point here, but we're going to run models in which this point is allowed to be anywhere in this square here. This is a vertical section, cross-section here, and this point 2 can be anywhere here. And the velocity can vary anywhere between 0 and 20 kilometers per million year, and the geothermal gradient can vary by almost an order of magnitude. So when we run that, this is the outcome of these inversions. What I'm showing you here are plots. Each dot in one of these diagrams corresponds to one of the 30,000 model runs. And the color of the dot tells us how well it fitted, it represented the observation. So warm colors, red, show low misfit, so good fit. Cold colors, blue, are low misfit, so they do not, high misfit, sorry, so they do not fit the data very well. And these plot here have on the axis here, one of the 6 unknown parameters for which we let vary through the optimization procedure. That's the geothermal gradient, the velocity, and then the X and Z position of 0.1 and 0.2. And finally, what I plot here, what I call the marginal distribution of the best estimate of each of these of the model parameters and how they fit the data. So where in searching through this, the optimization is trying to run more models, if you want, where this fit is low. And so this distribution is a very good measure of how well the value of that model parameter, this optimum value that we seem to obtain, is actually constrained by the data. If this distribution is narrow, it means that the value is very well constrained by the data. If the distribution is wide, the value of that parameter is not so well constrained by the data. So what do we see? we see that the position of point 2 is very well constrained. In fact, the position of point 1 is also very well constrained, although there seems to be a trade-off, a clear trade-off between x1 and z1. And that simply is that all the best fitting model have in common, sorry, I should come back here, have in common that this point 1 is along a line that aligns between point 2 and the edge of the model. So it's well constrained, but not its exact position, but the shape of the ramp is very well constrained. And finally, what's very interesting is that the velocity is also very well constrained. So let's see now what this means. Why do we converge well? We converge well in this optimization because we fit the data reasonably well. So what I'm showing here are the ages determined by Xiaoming, or the age elevation transects determined by Xiaoming in red, and in blue is the best model, if you want, the one that produced the lowest misfit predictions. And you can see that we represent the data extreme or very well, except maybe for one outlier here. Note here that we only run the model for 10 million years, so it cannot reproduce ages that are older than 10 million years. So to perform the optimization, all the ages that are older than 10 million years, we set them artificially to 10 million years. So it means basically that we're not trying to explain any variation in these ages that are older than 10 million years, but we force the model to try not to reset these ages, so not to produce younger ages than 10 million years, which is adequate for this scenario. And so how do we then explain the younging of the ages as we go north along as we go up? And then this is actually explained by, obviously, the position of the ramp is very important. The advection of the isotherms, due to the advection of the rocks closer to the surface is also important, but the most important factor to explain the younger edges here and the older edges there is the horizontal advection of rock. And you see, as we go towards the base here, once the rocks have crossed the isotherm that will set their age, they will have to travel horizontally much more when they are near the base of the plateau than they have when they are closer to the top. And I don't want to go into the details of this, but to express this is a similar plot where I show the distance, and you can see the topographic profile here in light blue. And what you see here, again, for a best fit model, are the helium ages that shows this gradual decrease of the ages as we go up the profile. And if I turn in solving the equation, the horizontal advection term, I don't get this gradual decrease of ages that I get with the advection term. So in other words, this trend that we see in the data that we can beautifully reproduce here with our model, or our best fit model, can only be achieved if due to horizontal advection. It's not the only reason, but it's a very important one. And you can see how we reproduce that in both the fission track data, the helium age, the helium appetite helium data. We get the trend right, but we also reproduce a lot of the detail that exists in the data that is just due there mostly to the topography, the present day topography. This is just focusing on specific data sets like the one by Repluma or the one by Yang. We don't do a perfect job. There's, for example, data that we don't reproduce so well. But overall, the misfit is very low and almost statistically, perfectly reproduce the data that is within uncertainty. What I found exciting about this result and this scenario, with Xiaoming, we have tried many other scenarios, and Xiaoping, of course, we have tried many other scenarios, and I will show you a few later, and none can fit the data so well, while also reproducing data that we haven't used for the inversion, for the optimization. And this is an example. What I'm showing you here is, again, latitude, and here I'm plotting velocity. So I remind you that in the model, another parameter that we inverted for is the velocity of the rocks flowing through this part of the world. And what I'm showing here are colored in green, the various values for each of the runs. So there's like 35,000 models here plotted here. The darker green shades corresponds to the best fit model. And what you can see is that they all converge nicely to a velocity between 9 and 11, 12 kilometer per million year. And on top here, I have plotted the station, GPS station velocities, southward velocities. And you see that even though we didn't impose that as a constraint to the data, to the inversion, we reproduce very nicely the horizontal advection velocity derived from the GPS data. Interestingly too, if we compare, again here, this is our best estimate for the ramp geometry. And if we compare that ramp geometry to estimate of the moho geometry in the area, we do a very good fit in reproducing the moho, which means that the step that we need to produce the velocity that we observe at the surface is likely to be a step in the moho, which makes sense. If you think that the topography is mostly of the plateau a function of crustal thickening in that area. Finally, we have some very would almost call them proxy for the geothermal gradient in the area, which has been obtained by Tang and co-worker by using electromagnetic data from which you can derive the depth to the Curie point from which you derive a geothermal gradient. So you see it's a very indirect estimate of the geothermal gradient in the area. But again, our best estimate of the geothermal gradient across that's something we get again out of the model fits very well the observations. And the large uncertainty here is due to the fact that as we go across the model, so these are model estimates, because the topography varies a lot in this part of the world, then the geothermal gradient will also vary a lot, and that's what is shown here. So I hope I now have convinced you that we have very simple way to explain all of the low temperature thermochronological data, to explain the GPS data, and to explain the paleoaltimetry data that tells us that the topography of the plateau has not really changed in the last 10 million years, with this simple model or scenario in which we assume that the topography and the step in the moho has been fixed for the last 10 million years. But this topographic difference drive the flow of rocks, which is also, of course, related to still the ongoing convergence of of India into Asia, drives those rocks across the surface and under a steady state or not changing topography. Note that what for us is important in reproducing the ages that we have observed correctly is the velocity of the rocks across this surface. We could, our result could be interpreted by saying, well, it's possible that the plateau and the ramp, the cross ramp, have actually shrunk or expanded over the last 10 million years. But then to fit the thermochron data, we would need a higher velocity, a velocity that is higher compared to this model by the same amount as we assume here the surface topography is migrating southward, or lower velocity for the rocks by an amount equal to the velocity by which we assume the plateau is shrinking northward. But the problem is then the velocity we would get here would not fit the GPS data. So to fit the GPS data, the velocity derived from the GPS observations, the best model is one in which the plateau is not changing its shape. We can test another scenario which kind of is physically not really satisfactory, in which the ramp is moving and the topography is constant, it's not moving, or the topography is moving one way or the other, and the ramp is moving, is fixed. And we've tested that, but it's not really satisfactory because you will end up with a topography that is not in isostatic equilibrium with the underlying moho geometry. But even though if we run an inversion, we can get a reasonably good match to the data, but it requires that the ramp is anything migrating northward, and it implies a very steep ramp, and a very cold geothermal gradient, which is not consistent with the present day observation. So we are kind of confident that this model is the one that is the most likely to actually reproduce the low temperature thermochronological data, the GPS data, the geothermal data, and the paleoaltimetry data. And so this is my conclusion. I will almost finish here, that the inversion we have done of a broad spectrum of low temperature thermochronological data from the area suggests that the southeastern Tibetan plateau has not really grown or shrunk in the last 10 million years. We should be very careful of it when we have evidence for exhumation to imply that it corresponds to surface uplift. When we interpret a lot of geological data, we must also, this is a clear example where lateral transport of rock is very important. And of course, it's very important here because we see from the GPS data that the horizontal component of velocity is of the order of 10 kilometers per million years, where the vertical component, the uplift or the exhumation, is less than 1 kilometer per million year. So clearly, it's a great place to actually, show that this lateral transport must be or can be very important. There's not much we can say about whether Asian monsoon has played a role. Maybe the fact that when the Asian monsoon increased in intensity about 10 million years ago, it's what actually caused the topography to become stable in steady state. But clearly, the data that we have, the thermochron data, is very hard to reconcile with any scenario that requires a southward propagation of the plateau. And finally, I want to come back to this point that I made about the control of topography on biodiversity, and come back to this paper by Ding et al. About alpine flora biodiversity observed all around the Tibetan plateau on the Himalayan side, but also in southeastern Tibet. And if we focus again on this area here of southeastern Tibet, here called the Hengduan Mountains, you see this is time again. So this is about 10 million years or so. This is the mid-Miocene here, and you see, if we look at speciation, right, which can be derived from phylogenetic data from a broad range or species of subspecies of these alpine plants, what you see is that speciation was very important, and especially by local recruitment and especially by colonization prior to the mid-Miocene, so pre-10 million years. And since 10 million years, the speciation has continued, but it's been mostly by what's called in situ speciation, and colonization, for example, has gone down as a mean to promote speciation and maintain or increase the biodiversity. And I'm not a real specialist here, but clearly the interpretation most in the field of this field make is that this is evidence for a growing topography, for a changing topography, which leads to creation of valleys, which are colonized by these plants. So the speciation is through the colonization of a growing topography, whereas this in situ speciation is more related to a fixed topography, in which maybe the climate is going to change, and especially maybe this monsoon intensification, and more recently, the quaternary, the rapid variation in climate and therefore in precipitation associated with the rash change in climate in the quaternary. So I'm not saying that we are explaining it, but our preferred scenario of a stable and not growing and not shrinking southeastern edge of the plateau seems to be very consistent with the mode of speciation and biodiversity evolution in that area, at least for these plants. And again, these plants are a good taxon to look at, because they depend on high elevation and moisture to actually exist and develop. So I will leave this and I'm more than happy to take questions. I don't know in which how you want to proceed, David, either with the chat or otherwise. I'm happy anyway.
Sure. Well, let's just see if anyone wants to jump in with a question. You can either raise your hand or just do it. Is there anyone out there with a question? silence or they're formulating. Oh, looks like Doug has a question.
Well, I was hoping a geologist would ask the first question, but okay. Hi, Jean. Nice
Hi,
to
Doug.
see you. So, wow, I hadn't really thought about horizontal advection of rocks ever, but I guess my question is really relates to what can perturb the steady state. So, I mean, obviously it wasn't always in steady state, the plateau. So what's more important? Is it the kind of pressure gradient, which seems to be from the left over from the collision of India with the Himalayas or something? Or is it the erosion rate? Which is more likely to perturb a steady state, I guess, is the question.
Yeah, I think that steady state is between uplift, or as I'm saying it, also horizontal advection of rocks, which across a dipping surface creates also uplift, okay, and erosion. And so it's a very interesting point that erosion is controlled by the shape of the landscape, by the slope, and by the climate through precipitation. So you're right. The perturbation could come from tectonics or from the climate. So I think there's little debate that the plateau itself has grown out of the Asian collision to reach, more or less its present geometry and elevation over the last 50, 55 million years. There's a debate not even know, was there a plateau even before the collision started, or some kind of topography? But we assume that the growth of the plateau is due to the collision. The question is, and this is where I find it very interesting, is there's evidence, mounting evidence, that it's kind of stopped expanding about 10 million years ago, or maybe sometimes say earlier, in that part of the world. And this is where you can say this steady state has been brought up. I'm not saying we have a perfect steady state, but we are closer maybe to achieving steady state now and stopping the growth of the plateau. Most likely because that part of the plateau now is growing into an area of very high precipitation, monsoonal precipitation. So that would be like the kind of first order explanation you could put in. But it could also be related to something stopping the growth because the ramp, the growth of the plateau due to the tectonic flux of material due to the potential energy of the plateau is actually also decreased. But this doesn't seem to be the case because we still see the rocks flowing. We still see the rocks flowing down the slope. Okay, so more likely that it's finally erosion that managed to actually keep pace with the rock motion.
Interesting. Okay, I'm going to think a bit more about that. Thank you.
But we know, sorry, just to make a very short point, we know that in some origins, smaller origins, like maybe Taiwan or New Zealand or the Olympic Mountains, we have strong evidence that this topographic steady state can be achieved. But I don't think, I don't think there's been evidence that how much horizontal advection can also be impacted by this.
Got it. Thank you.
Jean, George is here.
Hi, Georgie.
So in your PQ model, actually the whole entire crust is being displaced along the ramp, which is the mohole.
Yeah.
Can you compare that to the shear splitting in the mantle? How does it compare to that? And why would the crust actually flow along the mohole? Why would there be such a decoupling?
Yeah, so I have to be clear on something, is that because we use the thermochronological data to infer the amplitude of the velocity, we must, however, realize that the low temperature thermochronological data is only sensitive to what happens in the upper crust. So we cannot say anything really about the vertical structure and the velocity of the flow. What is interesting is that if you put the ramp, let it freely evolve, it comes up with a geometry that looks like the mohole. So that's why I'm saying it's likely that the whole mohole, the whole crust is flowing. But it could be that it's only the upper crust. And we don't know. I don't have any constraint from that data on the vertical structure. So, I would say the obvious thing is that, because of the thickening of the plateau, the lower crust has become hotter, weaker, and therefore allows this decoupling. But I cannot say from my modeling anything about the vertical structure in the velocities. It could be limited to the very upper crust. I don't know that.
Thank you.
Okay. Hi, Jean. This is Chris.
Hi, Chris.
Very interesting talk. Very nice. I wanted to ask you about something you didn't say very much about in the model, in the P-cube model, and that was that you didn't say how you constrained the distribution of both in time and space of the erosion. So was this considered in the model? And what do you think that had happened, to erosion distribution during that time?
So in this model, I have assumed that the topography has remained perfectly exact or the same as it is today for the last 10 million years. So if we look at the erosion has been the same everywhere since for the last 10 million years, because we know we have a flux of material and the topography is constant. Now, if you look, I don't have a slide, but if you look at the distribution of that erosion, just due to the geometry of the valleys, etc., it's roughly the same everywhere. But if you look at the integrated erosion, it's different from point to point because of this horizontal advection. And so I can quickly show you. Let me try to go out of this. I hope you can. No, I will go back to sharing the window in a minute, but I can show you. Here we go. So this is. I need to share again my screen. Click share screen. I'll leave it in this mode, but this is. Can I move this? Yeah, that's what I want to show you. I want to talk about the model relief surfaces, but this is actually the predicted ages, the distribution of predicted ages. And you see that the ages tend to be much younger in the valleys and much older. And sometimes these are not even reset in the interflows, let's call it that way, okay? So again, this is only true when we have a horizontal advection. If we don't have a horizontal advection, you see that the ages are much more uniformly distributed. So it means that the rocks here have seen the same amount of erosion. Like if you had a shovel, okay, you would have to remove the same amount of erosion everywhere. But the depth from which the rock comes is much more different depending on where you are. And so this is something that I don't think we are used, the frame in which we're used to work, because we don't usually consider the horizontal advection of rocks. But it is very important. And I'm not saying, no, obviously, this has not been the case. It is impossible to think that the topography has not changed by a iota over the last 10 million years. There has been a lot of relief change in that area. But it kind of may explain, for example, why you preserve these regions which have seen relatively little exhumation if they've seen a amount of erosion.
May I have a second question, or do I wait till later? Could you go back and put what you found in the context of Maureen Clark and Vicky Royden's work, but particularly on the work of the channel flow around the Sichuan Basin and to the south. So it's sort of the second part, the more detailed part of their work, because they tried to justify this on the basis that the surface wasn't moving. There was no evidence of deformation, and therefore they invoked the idea of channel flow at depth.
Yeah.
But I can see from your velocity field that you derived that the velocity is uniform across this region. And therefore you wouldn't get any deformation.
No.
And therefore you could be tricked into the idea of invoking channel flow. But you want to say something about the relationship here?
Yeah, the interesting point is that we don't see in this region any major thrusts, or equivalent would be an equivalent to the STD. Okay, so what I find interesting is that, you know, the fact that we see in the GPS data this velocity, to me means that if the whole crust, you know, if something is moving southward, it must be the whole crust. You can't have a strong shear anywhere in the crust, because it would show up when the rocks are exhumed, either as active faulting or as, you know, shear zones that are being exhumed, and we don't see that. So again, this is actually what led the work, and I will put it here, the work by Copley, to say that, look, we don't see that, and yet we see the GPS velocity. And for him, there is actually either a strong shear or not, depending on the way you are, but it explains why you don't see deformation, yet the strong upper motion of the crust seen in the GPS data. But I think, you know, you could still reconcile the GPS velocity field with the inflation model, so the lower crustal model, by saying that the material flows even faster in the lower crust than the upper crust starts flow. It still, you know, would work. You can still thicken the plateau and make it advance southwards, its shape, and having still the rocks flowing even faster on top. We tested that with, try to reproduce the thermological data, but we end up with a velocity of the upper crust that has to be, you know, very large, much larger than the observed GPS data to reproduce the low the thermochronological data. So that's why we don't see a way to reconcile the thermological data with the thickening model, the ongoing thickening and southward propagation of the plateau.
Okay, thanks, Jean. I may come back in a little bit.
Yeah.
Okay. Well, yeah, thanks a lot for an excellent talk. Maybe, I think there might be, are there any other questions? Maybe we'll leave it open for a little while, if that's all right. And if you guys want to catch up and talk a little more, that's okay. But I just want to say thank you now for a really interesting presentation.
Yeah, thanks a lot for the invitation, and it's nice to see a few faces that I know.